Hello, everyone. This recording is going to cover part of Module 14 in Physical Science. And Module 14 is on waves and sound. And then the next module that we'll cover after Module 14 is covering light waves. So we'll talk about waves in general in this chapter, and then we will talk about light waves at a later time. So the thing to remember about waves is that both light and sound can be described as waves. There are different types of waves, but both of them can be described as waves. So let's start by looking at a figure. Okay, so the figure that is going to come up here is a figure of a transverse wave. And you'll notice that in a transverse wave, the highest points of the wave are called the crest. So the highest points, this is a crest, a crest, a crest. And the lowest points of the wave are called a trough. So a trough, a trough, a trough, a trough. And then the distance between one crest and the next crest is called the wavelength. And the symbol that is used for that is the Greek letter lambda. Okay, so that's the Greek letter lambda that is used for wavelength. So wavelength is either from peak to peak or trough to trough. So it's the measure of one wave measured either from peak to peak or trough to trough. That's wavelength. And then another variable that is measured is the amplitude. And notice that for the amplitude, we kind of have this imaginary line that runs through the middle, and then the amplitude is measuring from that line in the middle to the crest. So it's the height of the wave. You could do the same thing. You could also measure in a downward direction, and you'd get the same thing. So it's just measuring the height of the wave, and we call that amplitude. And then the other thing that we measure is frequency. And frequency is how many waves you get per second. So the number of waves per second. So for example, if we had a wave that looked like this, and then if we had a wave that looks like this one, obviously there are more waves per second because they're closer together. So this second one would have a higher frequency, and this one would have a lower frequency. So the number of waves per second is frequency. The other thing I want to show you is the relationship between frequency and wavelength. Okay, so frequency is how many per second, and wavelength is, again, peak to peak, peak to peak. So what you should see from this is as you increase frequency, so as the waves become, as you have more waves per second, what does that do with wavelength? Well, it decreases wavelength. So in other words, we would say that wavelength and frequency are inversely proportional to each other. As you decrease frequency, which we would see here, then the waves, as frequency decreases, the waves become farther apart, and so the distance between from peak to peak becomes longer. So as you decrease frequency, you increase wavelength. Okay, so again, frequency and wavelength are inversely proportional to each other. Frequency is small, wavelength is large. If frequency is large, wavelength is small. Mathematically, we express the relationship between frequency and wavelength like this. So frequency is equal to the speed of the wave divided by the wavelength. So the letter F is used for frequency. We use the letter V for speed. I know that we've also used that for velocity, and have had to, with velocity, you have to indicate a direction, but it's also used for speed, and in this case, you don't have to indicate a direction. And then the symbol for wavelength, remember, is that Greek letter lambda. So frequency is equal to speed divided by wavelength. Speed is measured in meters. Speed is measured in meters per minute. So we have meters per minute divided by, and the wavelength is measured in meters. So it's meters per minute divided by meters. And what that means is that the meters divided by meters is, speed is measured in meters per second, not per minute. So speed is in meters per second for waves. Wavelength is measured in meters. So you have a meters on top and a meters on bottom. Well, meters divided by meters is 1. And so the unit that you end up with for frequency is 1 over second, or we would say this 1 per second. So in other words, a frequency of, if our frequency was equal to 2, 1 per seconds, that means that there would be 2 waves every second. However, instead of keeping that unit as a 1 per second, we call it a hertz. And that's named after the man who discovered radio waves. So frequency is in the number of waves per second, so it's 1 per second. But instead of saying 1 per second, we measure it in hertz, and the abbreviation for hertz is Hz. there are two types of waves. The first type is a transverse wave, and it's actually the type that I drew up here before. And in a transverse wave, I'm going to introduce two terms here, but I'll explain these. In a transverse wave, propagation and oscillation are perpendicular. So let me explain what that means. So if you think of the waves in the ocean, so the waves go up the waves in the ocean go up and down, right? If you stand on the shore, you can see that the water goes up and down. This up and down motion is referred to as the oscillation of the wave. Okay, but then we also know that in addition to water waves moving up and down, they also are moving forward at the same time. So they're going, they're moving toward the shore. So and we call that propagation. So they're moving, the waves are moving toward the shore, which would be in this direction. But at the same time, they're going up and down like this. So that's in that direction. So they are moving, the propagation is going this way, the oscillation is going that way, so they're perpendicular to each other. So that is called a transverse wave. And light is besides the waves in the ocean, light is another example of a transverse wave, and we'll look at that in Module 15. And the other type of wave is a longitudinal wave. And in a longitudinal wave, the propagation and the oscillation are parallel. So in other words, the direction that the whole wave propagates, the whole wave moves, is the same as the way the individual parts of the wave move. So propagation and oscillation are parallel. So the best example of this, and it's unfortunate that we can't look at this, we'll look at it when we do get together in class. If you've ever played with a slinky, that is a good example of a longitudinal wave. And I will say right now that sound is also a longitudinal wave. But let me show you a figure of a slinky and show you how it is an example of an example of a longitudinal wave. So if you've ever played with a slinky, you know that in a slinky you get the little wire components. They compress each other, so they become compressed, but then they spread out. Okay, so those those are called compressions and rarefactions. That's not that important, but the important thing is that these compressions and rarefactions are moving in this direction, right? And then at the same time, the slinky as a whole is also moving in this direction. Okay, so this would be the oscillations of these individual wires, as it were, in a slinky are in this direction. And then the slinky as a whole also moves in that direction, so that's the propagation. So the oscillation and propagation are parallel to each other. So that is an example of a longitudinal wave. Okay, so let's do a few problems related to our equation that frequency of a wave is equal to the speed divided by the wavelength. Okay, so in the first problem that we will do, we are going to say that a wave is traveling at 3 meters per second. So that'll be its speed. And it has a wavelength of 0.5 meters. So that's its wavelength. So then what is the frequency? Well, frequency is equal to the speed. So it would be 3 meters over seconds divided by the wavelength, which is 0.5 meters. Okay, so we have a unit of meters on the top and a unit of meters on the bottom. So meters divided by meters is 1. So our units that we have is 1 per second. Remember, that's called a hertz. And then if we do the math, 3 divided by 0.5 is 6. So our answer would be 6 1/seconds, or we use the unit hertz for 1 per second. So that what this means is that if you are standing in the middle of this wave, every second you're going to get hit with 6 waves. So if you think about standing in the ocean, if you're standing in the ocean and the waves are coming in and hitting you, if the frequency of that wave is 6 hertz, then you will get hit by 6 waves every second. Okay, let's look in your book. If you want to turn in your book to the On Your Own 14.1, and that is on page 344. It says that a longitudinal wave is suddenly stretched so that its wavelength, which is lambda, increases. If the speed of the wave does not change, what will happen to the frequency? Okay, so we said earlier that wavelength and frequency are inversely proportional. So if you increase wavelength, then that means that you would decrease frequency. Okay, so wavelength and frequency inversely proportional to each other. Okay, then let's look at On Your Own 14.2. Suppose you are wading on a beach that is experiencing waves that move with a speed. So speed is the letter V, 0.5 meters per second. and they have a wavelength, so that's lambda, is equal to 0.25 meters. What is the frequency? Okay, so again, frequency is equal to speed divided by wavelength. So 0.5 meters per second, meters over seconds, divided by 0.25 meters. So we have meters divided by meters, that's 1. And then if we do the math, so 0.5 divided by 0.25 is 2. So our answer would be 1 per second, or 2 hertz. So again, that means that if you're standing there, 2 waves will hit you every second. There are a number of experiments in this chapter that unfortunately for now we will not be able to do. However, we will do as many of those as possible when we meet again in person. So the first couple of experiments deal with sound waves, and the first couple of experiments are designed to show you that a wave needs something to travel through. So in other words, we say that a wave requires a medium. It requires some substance for it to travel through. And so when we talk about waves oscillating, what it oscillates, when that wave oscillates, it means that it is oscillating or causing a certain medium. It travels through a certain medium. And the medium that sound travels through usually is air. When the sound wave travels, it oscillates the air as it travels through it. Let's look at the human ear, and we can see how that happens. Okay, so this figure is showing that as the sound waves leave this person's mouth, those sound waves travel through the air, and as those sound waves travel through the air, so they oscillate the air, and then they hit. They go in your outer ear, and this is called your middle ear, or your middle ear canal, and then they hit this structure right here, which is a thin piece of tissue that is called the tympanic membrane. We sometimes refer to this as the eardrum. And then, so when those sound waves hit the tympanic membrane, they cause that tympanic membrane to oscillate or to vibrate, and then those vibrations get sent to the small ear bones. There's three small bones in the inner ear, those will start vibrating, and then those bones are connected to this sort of coiled structure in the ear that is called the cochlea. And that these vibrations then get sent to the cochlea. And what the cochlea does is the cochlea changes those vibrations into electrical signals. And those electrical signals are then carried on nerves to the brain. And then our brain then interprets those sounds. So movement of oscillation of the air due to sound vibrates the tympanic membrane. That causes the inner ear ossicles to vibrate or oscillate, and then it gets transferred to the cochlea. The cochlea turns it into electrical signals, and then those electrical signals travel on nerves to the brain. And I want you to see here that the sound waves oscillate the air, and then at the same time you have the sound waves oscillate in this direction, but then they also move in the same direction. So sound is an example of a longitudinal wave. So the propagation is parallel to the oscillation for sound waves. Another important characteristic of sound is how fast it travels, and we'll do an experiment in class to try to measure the speed of sound. But the equation that represents the relationship for the speed of sound is this. Okay, so first of all, unlike some other equations, this part of the equation is in parentheses, doesn't have any units, and you'll see why that is in a moment. But however, the speed of sound is expressed in meters per second. We've already been using that unit before. So what does this T mean? So this is a constant, so that's part of the equation. That doesn't change. This T stands for temperature. So in other words, the speed of sound depends on the temperature of the air or whatever other medium it is traveling through. So, and the other thing to remember is that in order to use this equation, the temperature has to be in degrees Celsius. Okay, so degrees C. You can't use it, this equation, if it's in Fahrenheit. The temperature needs to be in degrees Celsius. So let's look at a problem. If the temperature is 86 degrees or 68 degrees Fahrenheit, which is, pretty standard temperature of a room, and that is equal to 20 degrees Celsius. What is the speed of sound? Okay, so our equation for speed of sound is 331.5 plus 0.6 times the temperature, and we don't put any units on there, and then our answer is going to be in meters per second. So remember, we always do multiplication before you do addition or subtraction. So 0.6 times 0.2, or I'm sorry, 0.6 times 20 is 12. Okay, so then it's going to be 331.5 plus 12. So the velocity is 343.5, and the units are meters per second. Another thing that you have probably heard about is that when there is a thunderstorm and there is thunder and lightning, you will see the flash of lightning before you hear the clap of thunder. And the reason for that, the flash of lightning and the clap of thunder are occurring at the same time. However, light travels very, very fast, and it travels so fast that we, essentially see it the minute that it flashes. But sound travels much slower than light, so a period of time passes between when we see the lightning and when we actually hear the thunder due to the slower speed for sound. So we can actually, if we know when we hear, if we time when we hear the clap of thunder, and if we know the temperature of the air, we can determine how far away the lightning was. So for example, let's say that you see a flash of lightning and then the thunder occurs 2 seconds later. And we'd like to know how far away was the lightning. So, and also I guess I forgot to tell you that the temperature outside is 15 degrees C. So it's a little cool, but it's not, wouldn't be unusual for a temperature when a storm is taking place. So you can figure out the speed of the sound. So our equation for the speed of sound is 331.5, and we'll 0.6 times 15. Okay, so 331.5, 0.6 times 15 is 9. So the velocity of the sound is 340.5. And remember that units are meters per second. Okay, now that we know the speed, and we know that it took 2 seconds for that sound to travel, then we can figure out we can figure out the distance that it traveled. So speed is equal to distance divided by time. So we know the speed and we know the time. So what I'm going to do is just solve this equation for distance. I want to get distance by itself, so I'm going to multiply both sides of this equation by time. So time times speed is going to equal distance. Let me erase all of this. So speed, as we did this when we were looking at velocity, speed is distance divided by time. So that means that speed times time is equal to distance. Okay, so what we had calculated for speed was 340.5 meters per second, and we said that it took 2 seconds from the time we saw the lightning flash until we heard the clap of thunder. So here we have a second on the bottom and a second on the top, so those are going to cancel, and our units that we'll be left with will be just meters. So 340.5 times 2 is 681 meters. So at this temperature and a delay between the lightning and the thunder of 2 seconds, that tells us that the lightning is 681 meters away. Let's do a couple more problems of those. So let's do on your own 14.3. What is the speed of sound in air when the temperature is 28 degrees Celsius? Okay, so again, our equation is 331.5 plus 0.6 times the temperature, and we said it was 28 degrees Celsius. So the velocity is going to be 331.5, 0.6 times 28, .6 times 28 is 16.8. So adding those together, the velocity then is 340.5, and we remember I'm sorry, 348 should be 348.3 meters per second. Okay, so at an air temperature of 28 degrees Celsius, the speed of sound will be 348.3. So I hope you're seeing here that as you increase temperature, so as this number increases, you're going to increase the speed of sound. So sound travels faster in warmer temperatures than in colder temperatures. Okay, so now let's look at on your own 14.4. Okay, so this one says that during a thunderstorm, the temperature is 18 degrees Celsius. If you see a lightning flash and hear the thunder 1.5 seconds later, how far away was the lightning? Okay, so we will start by figuring out the speed of sound. Okay, so 331.5 times 0.6 times the temperature, which is 18 degrees C, and therefore that's 331.5 plus 0.6 times 18 is 10.8. So we add those two together, so the speed of sound is equal to 342.3, and the units are meters per second. Okay, then we said that speed is equal to distance divided by time. So speed times time is equal to distance. Okay, so our speed was 342.3 meters per second. The time that we were given between the lightning and the thunder was 1.5 seconds. Okay, so our seconds are going to cancel, and we'll be left with a distance in meters. So 342.3 times 1.5 is 513.35 meters. So the lightning flash occurred 513.35 meters away. Okay, this table shows us how, so we've talked about sound traveling in air, but you probably also realize that sound travels through substances other than air. Otherwise, we wouldn't, we hear sound. If somebody is in a room, we can hear sounds from another room. If somebody's playing TV or music and we're in a different room, we can hear that sound, and that's because the sound can travel through the walls. So anything that any medium that sound can oscillate, that sound waves can oscillate, it will travel through. So this table shows us the average speed of sound. Well, I guess it's giving us the speed of sound in different substances, and for air, we're assuming a temperature of 25 degrees Celsius. So what I want you to see here is that air can travel through, or sound can travel through liquids, and it can also travel through solids. So as you look at this, you'll notice that the fastest speeds of sound are for solids. So wood, steel, aluminum, iron, and glass. So these speeds of sounds are in the 5,000s, and this one's almost 4,000. So sound travels fastest in solids. Then you'll notice if we look at alcohol and water, those are liquids. So it travels second fastest in liquids. Here it's traveling at 1,400 meters per second, 1,100 meters per second in liquids. And then sound travels the slowest So air is in the gas form, right? So sound travels slowest in gases like air or other gases. So the important thing here is that sound can travel through substances other than air, and in fact it travels faster through both liquids and solids than it travels in air. Okay, I think we'll do one more thing, and then we'll stop for this particular chapter. So when something travels faster than the speed of sound, you've probably heard this term, it's called supersonic speed. So that is faster than the speed of sound. So jets often can travel faster than the speed of sound, and we use a term that is called Mach. So if something is traveling at the speed of sound, we say it is Mach 1. So that's at the speed of sound. And remember, the speed of sound varies depending on temperature. So as a plane is flying through the air, the speed of sound will depend on the temperature of the air. So at speed of sound, that is referred to as Mach 1. If a plane is traveling at Mach 2, then that would be that it was traveling 2 times the speed of sound. And then Mach 3 would be 3 times the speed of sound, etc. And it doesn't have to be just whole numbers. You could say Mach 1.8, which means that is traveling at 1.8 times the speed of sound. So that that term Mach is used to compare the speed of an object to the speed of sound. And you probably also know that when an object travels faster than the speed of sound, it produces a sonic boom. And then let me show you what happens to produce that sonic boom. Okay, so this figure is showing a jet traveling through the air. And when that jet is traveling through the air, it also produces pressure waves. So that it's pushing on the air and it's producing pressure. And as long as the jet is traveling slower than the speed of sound, so less than Mach 1, then the pressure waves are traveling in all directions, including in the front of the plane. But then when the jet reaches Mach 1, so when it reaches the speed of sound, it begins traveling at the same speed as the pressure waves. So the jet is traveling at the same speed as these pressure waves. And so what will happen is those pressure waves will kind of bunch up here in front of the plane, and that produces a shock wave. And then when the jet gets faster than the speed of sound, the jet actually is now moving faster than these pressure waves, and you have this cone-shaped shock wave, and it produces a very loud boom. So it's like just a loud boom, like a thunderstorm. So it's just these huge sound waves moving through the air. And those sound waves can damage the human ear, but they also can damage buildings. So usually planes are not going to fly at speeds greater than Mach 1 if they are over a densely populated area where there's a lot of buildings. So we usually only fly at speeds greater than the speed of sound if they are in very like sparsely populated areas. Let's look at a couple on your own, and then we'll finish for today. So let's look at on your own 14.5 in your textbook. And what that says is, on the page, 14.5 says, remember from Module 9 that the outer core of the Earth is liquid, but the inner core is solid. If a geophysicist is studying how sound waves travel through the core, would he expect the sound waves to travel faster in the inner core or the outer core? So the outer core is liquid. The inner core, we remember, is solid. And so since we know that sound travels faster in solids than in liquids, then sound would travel faster in the inner core than it will in the outer core. Okay, then the last thing we'll do is on your own, 14.6. So this says a jet is traveling at Mach 1.8. When the temperature is 0 degrees C, what is its speed in meters per minute? Okay, so we first have to know what is the speed of sound, because Mach 8 means it's traveling at 1.8 times the speed of sound. So the speed of sound, our equation is 331.5 plus 0.6 times the temperature. In this case, the temperature is 0, so 0.6 times 0 is 0. So the speed of sound at 0 degrees C is 331.5 meters per second. So then Mach 1 would be 1.8 times that amount. So 331.5 times 1.8 is 596.7 meters per second. Okay, so we're going to stop there for Module 14. We'll pick up there next time and cover the rest of this chapter. I would like you, before we meet again, which will be on March 31st, that's going to be after spring break, in the study guide, so before we meet again, so by March 31st, if you do these this week, you won't need to worry about doing them over spring break. I'd like you to make sure that you do, this is on page 365 in your textbook. I'd like you to make sure you try problems numbers 3 and 4 and 5. And let's do try to do number 8 and 9. And let's do number 11, 12. Okay, so these are all problems that you can do that are like the problems that we covered today. So on page 365, the next time, on the next recording, I will do the solutions to problems 3, 4, 5, 8, 9, 11, and 12. So it would be good for you to try to do those on your own before you watch the next video on March 31st.